Hey there, seniors. I'm going to give you a brief little introduction to impact craters because we're going to be playing with impact craters in terms of calculations and data collection for the next couple of days, and hopefully you'll get a chance to watch this before tomorrow, right? So anyway, really briefly, I'll go through this as fast as I can. There's a lot we can learn from impact craters on the Earth and on other planetary bodies. Now, you are probably very familiar with craters from a certain standpoint. You know, an object comes in at usually kilometers per second, some really crazy velocity. The impactor itself is going to have certain characteristics that are measurable: mass, variable mass, volume, density, and so on. As you can see here, and as it's coming in very fast, it's going to, of course, impact some kind of a surface. Typically, we think of it as a solid surface, like say a continent on Earth or any other planetary body, any other piece of land on that body. It can also impact water. Of course, water is only so deep, so eventually it will, of course, impact solid Earth as well. The Chicxulub impact that sort of was part of how the dinosaurs met their demise, along with flood basalts erupting. That impact landed in the water, but yet made a huge crater. It's buried now, but nevertheless it did. So there's things we can calculate directly about the impactor and about the crater itself. And then from these things, there are calculations we can make about the effects of a potential impact or the effects of a past impact. So that's really what we're going to be getting to. We're going to use some calculus tools to help us with that next time around. There are different types of impact craters, and these, of course, are dependent upon these variables here for the impactor, but also the type of material being excavated. So, what kind of material is the impactor hitting? But really, it's all about the diameter and the size of the object itself. So, you can have things as tiny as a pit. That's a little 10-micron pit, like a micrometeorite impact, all the way up to a simple crater. These are all on the moon, 1 kilometer in diameter. Euler crater, which is 28 kilometers in diameter. To Schrödinger will come up here later, which is a peak ring basin. Crater basins are much, much larger. So 320 kilometers is big. And then multi-ring basins. And then, of course, usually the energy is radiating outward in all directions from the impact event. And so those are the biggest ones. But diameter is what we then measure. So the diameter of the object is important, diameter of the crater is important. Now, of course, it's not always the same on every planet. There's a transition between each of these steps of different kinds of craters that are dependent upon the gravitational pull on that planet. And so this diagram here illustrates that planetary gravity on the x-axis with the transition from crater diameter to the different types of craters, from simple to complex mainly. But you can see the Earth, the transitions down here at our gravity, but at a certain crater diameter, it goes from simple to complex. And on the moon, it's a much greater diameter to go from simple to complex, again, because the gravity is so different. Okay, so some of the variables that are important to us are things like the variables that affect the two objects. Newtonian gravity, these objects are attracted to each other, and the gravity of the impacted object and the gravity of the mass, the gravity of the impacted object, the mass of the impacted object ultimately matters. Simple craters have a pretty simple morphology. As in any impact crater, there's the actual crater that's created during the event itself, which is the actual excavation of material and the melting of some material as well. And then there's what is actually left for us to see once the dust, or ejecta in this case, settles. So simple craters are just that, simple craters, collection of stuff at the bottom of the crater, slump material from the sides and so forth. No central structure. Melted stuff has gone away, and so forth. So complex craters are a little different. You have this peak in the center typically that rises up. You might have some molten material that collected between the peak and the rim of the crater, but these are much bigger in diameter. Typically they'll have a ring and there'll be a peak in the center. Impact basins, the really big ones like Schrödinger that I mentioned before, these have a particular morphology, and they're so big that you can actually get down, the impact actually impacts the mantle to the point where you can actually have eruptions of basalt from the magma from below, which is what's happened in large part on the moon's surface. When you see the man on the moon, so to speak, you're looking at darker areas. With the moon itself is pretty bright because of the anorthosite feldspar, but the impact basins are dark and they look like eyes and whatnot, right? But because those are filled with mare basalts, erupted material. So that's mantle material off of the moon. Looks like Earth's mantle material is also basaltic. And then, of course, you have impact breccias, which is really, you know what breccias are? Really fragmented stuff, fragmented sediments all lithified together, like conglomerates, but just with angularly shaped particles. Because these are really intense impacts, very impactful. Lots of cracks, lots of broken stuff, and so forth. We can tell the age of a surface. Now, I'll go back to this beginning slide here. What I meant to say here was one of the great tools of impact craters is we can count craters on a surface. We can tell that this surface on the southern part of the moon here is older because of the number of craters on it, and this surface up here is younger because of the relatively few craters on it. That is an important way we measure age, and part of that's because in the early part of the solar system, there was a lot more impact cratering going on as planetary accretion was going on, as planets were growing and objects were slamming all around. Things have largely been cleared since then, and so we know that there's been fewer impacts. There's still impacts, but not like there once was. And of course, the moon itself, come to this later, is a result of an impact as well. So moving back on over here. Another way we can tell the age of a crater itself is by looking at, this is on the moon specifically, we would have to create a different table, a different graph like this for any planetary object, again, based on gravitational pull. But you can pause here for a minute and look at how crater diameter and relative age are related. Copernican is the oldest period of the moon, and then the Imbrian is the youngest here. Oh, I may have that wrong here. Lunar, geologic, time scale. I may have that backwards here. I'm looking it up real quick here. Copernican's the more recent stuff. I thought I had that backwards. Imbrian is the oldest stuff, so you can see what kinds of craters were created during the oldest part of the moon's existence. Sorry about that. All right, crater ejecta. So it's not just the crater; it's the stuff that's spewed out of the crater that also matters to us. This is pulled from a model of an impact crater on the moon, and you can see the dusty stuff. But the dusty stuff is only part of the story. There's big boulders too, and so these big boulders. The big stuff is also not moving quite as fast. It doesn't go as far, right? You can kind of see these are particle sizes, relative particle sizes. You can see that this is taken from out here. So this smaller scale stuff, along with the melted yet then recrystallized material, is carried out much further, but smaller particles go out much further, which makes sense, right? So this is the ballistic sedimentation. So these are objects that are like mortars in a battlefield, right? You're shooting out in parabolic courses, and they, from the impact itself, all in 360 degrees around it. Now, if the impactor is straight on, this is what we're imagining. Now, if it comes in at an angle, of course, the impact eject is a little different. It goes further in some places than it does in others, but you can imagine that in your head, I hope. And we'll have a simulator that'll help us imagine that as well. But this is objects that are out here. They're flying out here to this range at about 2 times the time of the impact, and so forth as we go further out. All right. So around a simple crater, ejecta morphology typically contains these 4 items here, and you can see where they're pointed out in the various structures here. We'll get to rays. Rays, you don't see them here. Well, you see them. You can see radiating out of here are crater rays, and that's just a result of the ejecta deposits going off in all 360 degrees. The ejecta velocity is, or I should say, the ballistic range is a function of velocity. So if you want to know how far an object is going to go, you have to know how fast it's moving. Most ejecta moves at 45 degrees. We know that, generally speaking, and so we can pretty much know how fast an object was moving based on the size of the object that was moving. here on Earth, we've done this. We've done it. The study was done where they looked at the total ejected mass, or they can actually calculate the total ejected mass of an impact based on the largest fragment. So if you can get the mass of the largest fragment that you can find, then you can calculate the total ejected mass. Super, super useful, because all I have to do is find the biggest darn rock that came out of that impact, and I can figure out how big that whole impact was based on how much was removed. Well, we're going to use calculus for that, but you can do that just by finding the biggest boulder. And so we've done that. Somebody did this for Meteor Crater, and you go do a survey of boulders, like go find boulders and figure out how big they are. Talk about fun field work. Nobody hired me for that. I would have loved to have just walked around in the desert looking for big boulders. That'd been a lot of fun. Whoever did that had a great time. So, okay. Impact sediment, collections of sediment tend to be a little different than your typical sediments. So here we have some sediment samples from various locations: dune sand, loess, just general dust floating around in the air. And you can see what the particle diameter down here versus the cumulative weight percent. So you can see that depending on the sediment type, most sediment types are on Earth. Like we think about like sediments that we've looked at in class, for instance, right at the beach or whatever. Here's your beach sands right over here, and your desert sands. You can see they don't have a lot of big stuff. This is the big stuff down here, and they ramp up real fast in the sand size area, and then they kind of, by the time you get to like 90% of the sample or 80% of the sample, you're only then just getting to the small stuff, right? And so loess is really fine grained stuff. It's a little different. Ramps up real quickly up until the silt size stuff, and then it tapers off more slowly because you're still getting a lot of clay in loess. Because loess is sand and is clay and silt. That's wind blown. Anything wind blown is loess. So, you're used to sediments that are like that. Now you look at like impact sediments, and you got a ton of boulders, big ones. Look at it, big. I mean, it ramps up fast in some of these cases, and before you even get to silts and so forth and dust, you're already hitting 80% of the sample. So while maybe we think of ejected deposits primarily in the sense of them being dust, I mean, it takes a lot of dust to make up the mass of a single big boulder, right? So we're talking about cumulative weight percent of particle size, where it is what it is. But the boulders are the big part of the story, really. And this is just a great shot of ejector rays taken by the HiRISE instrument. It was looking at the moon. All right, speaking of our moon, the biggest impact that I can think of is the one that formed our moon. Earth didn't initially have a moon. Earth actually would have been smaller once upon a time than it was. And this is about 4.5 billion years ago. Around 4 billion years ago, this object, it's been different models of formation have been proposed, and the reason they've been proposed is because Luna, our moon, is just that much. Is really big for the size of the Earth, and compositionally, the two have a lot of similarity, and so it's often been hypothesized that the two were formed at the same time, perhaps through an impact or perhaps through, the pulling off of material. But anyway, the impact hypothesis is the favored one at this point, in fact. So an object we refer to as Theia impacted the Earth, and then once it impacted the Earth, it took a while for consolidation to occur, redifferentiation of the bodies to become the newly formed moon and our planet. And in the last few years, we've discovered these things called large low shear velocity provinces. There's two of them near the core mantle boundary, antipodally oriented from one another. And these are, in large part, playing an interesting role in how we understand our Earth's interior in terms of where subducted slabs go and where mantle plumes that form like the Hawaiian hotspot come from. We think these are the source of mantle plumes. So Theia, from 4 billion years ago, is still giving us places like Hawaii in that regard. So these may be what's left of Theia. We don't know for sure, of course. That's a hypothesis, but it's a really compelling one. So anyway, that's where our moon comes from. So, all right, I hope you enjoyed this little introduction, and when we get in class, we'll we'll dive a little deeper. Thanks.